This afternoon we will be talking about integration by partial fractions. Question: when do we use integration by partial fractions? Okay, we use integration by partial fractions in integrating rational expressions. Okay, here we have the numerator p of x divided by the denominator q of x dx. Okay, what are the basic integral formulas we have here? The first is x to the n. The integral of x to the n dx is actually x to the power of n plus 1 over n plus 1 plus c. So what does this mean? Okay, if you have a variable x to a certain exponent n, to integrate that we add 1 and then divided by n plus 1, whatever we will get on the exponent, and then of course plus c. And the second one here is the integral of 1 over x dx is actually the ln of the absolute value of x plus c. What does this mean? This means that if the numerator is actually the derivative of the denominator, the integral of that is just the natural log of the absolute value of the denominator. And we have here another integral formula: 1 over x squared plus a squared dx. Okay, the integral of that is given by 1 over a inverse tangent x over a plus c. And here another integral formula is the integral of k times f of x dx is actually k times the integral of f of x dx. So this means we can actually pull it outside, up front. Okay? And the last integral formula we have in here is the integral of f of x plus or minus g of x dx equals this one here. So the meaning is, if we are going to find the integral of the sum of two functions or the difference of two functions, we can actually find the integral of its piece, the first function here, and then plus or subtract, okay, the integral of the second function. Okay, let's proceed. Now, in integrating rational expressions, I find 4 cases. So case 1, I call it when the degree of the numerator is greater than or equal to the degree of the denominator. Okay, that's case 1. Okay, we have an example here. We call it example 1. We have here the integral of x cubed, okay, and so on, divided by x minus 2 dx. Notice in here that the degree of the numerator is 3 and the degree of the denominator is just 1. So this falls under this case. So what shall we do? Long divide, or simply apply long division. How do we do the long division? This one. How do we do the long division? Okay, first we will set it up. Okay, the numerator, which is x to the power of 3 plus 2x squared minus 3x plus 1 will be on the inside, and this denominator will be on the outside, like that. What shall we do first? Okay, the first term here, x cubed divided by x, that is x squared, we write our answer on here, and then multiply that. X squared times x is actually x cubed. Then x squared times negative 2x. Then again, first term here divided by the first term here, 4x squared divided by x. That's going to be positive 4x. and then multiply that. 4x times x is 4x squared, and then 4x times negative 2, it's negative 8x. Then again subtract. When we subtract that, okay, it becomes 5x. Next, we bring down the last term there, 1. Again, first term divided by the first term again, 5x divided by x is just a positive 5. And then 5 times x is 5x. 5 times negative 2 is a negative 10. And then again subtract, this will give us 11. So this is our remainder. How do we deal with this remainder? So we are going to put the remainder in here and then over the divisor, which is x minus 2. So we have x squared plus 4x plus 5, okay, dx plus 11, the integral of 1 over x minus 2 dx. Okay, I break it up into two pieces because I see that this is just a plain polynomial and this is another rational expression. So that is okay, in accordance with this rule here. Okay. The last one, we can break up the sum or the difference of two functions, and then when I pull up the 11, it is in accordance with this one here, that if we have a constant, we can actually pull it up front. Okay, so now we are ready. Okay, of course, the integral of x cubed is just, x squared is just x to the power of 3 over 3. And then for x squared, the exponent here is 1 plus 1 is 2 divided by 2 is, 4 divided by 2 is just 2 actually, that is just 2x squared. And of course, the integral of 5 is just 5x. And now, plus 11. And we have here 1 over x minus 2. You know that the derivative of x minus 2 is just 1, which is the numerator. According to one of the rules here, we have this second rule. It says it's just the natural log of the absolute value of the denominator. So we'll do that. Okay, this means this is just ln x minus 2, the absolute value of x minus 2, of course, plus c. Okay, that's the first case. Now, we'll go and do case 2. Okay, what is case 2? Okay, case 2 is, that is when the degree of the numerator is less than the degree of the denominator, and denominator is factorable into distinct linear factors. Okay, to motivate this, remember that if you are going to add 1 over x plus 3 over x plus 1, the first thing we are going to do is find the LCD. And in this case, the LCD will be x times x plus 1. Alright? And then, if you already find the LCD, you know, because the LCD is x and x plus 1, on this side here we need x plus 1 over x plus 1. And on this side here we need an x over x. So now when we are going to multiply this here, it will only be x plus 1. Over, when we multiply this, of course, it's x squared plus x. And then when we multiply this part here, 3 times x is 3x. Of course, denominator is x squared plus x. Okay, it will give us that one. Now, if we simplify this part here, x plus 1, the numerator, plus 3x, we will have 4x plus 1 and over x squared plus x. We would like to write this form here to this form here. Go back to that form. Okay? And the way we do that, okay, the process of doing that is actually what we call the partial fractions decomposition. Okay, now we will have an example here. That one. Okay, the degree of the denominator is greater than the degree of the numerator. So this is case 2. So, and the denominator is factorable into distinct linear factors. So how do we do that? Okay, we do that in here. That's number 2. Okay, so what are the factors of this one here? Factor of 2x squared, 2x cubed plus x squared minus x. Of course, we have a common x here, so that means we have 2x squared plus x minus 1. And it looks like this quadratic trinomial here can still be factored. Okay, for 2x squared, it's going to be 2x and x. And now for factors of negative 1, that is plus 1 and negative 1. Okay? So these are the factors. We assume that there are constants a, okay, over the first factor x, plus another constant b over the second, one of the factors actually x plus 1, plus another constant c over, okay, the other factor 2x minus 1, such that when you are going to add this part here, will give you this one. So that's our concern now. So how do we solve it? Of course, if we are going to multiply all the terms here with this great denominator, so when we multiply it here, everything cancels out, you will only have 1. If you are going to multiply this to this term here, you will have a x plus 1, 2x minus 1. And of course, if you are going to multiply the same, okay, polynomial to here, you will have b and then x, 2x minus 1, and of course plus, I'm sorry, we don't have enough room here. When we multiply the same, okay, polynomial to here, you will have c and then x plus 1. Alright? Now, how do we find values of a, b, and c? So, we can actually assign what we call clever values. Okay, what are they? Okay, the purpose actually of using clever values, okay, actually clever values of x is to zero out some of the terms here. Okay, for example, we will let x to be, for example, 0. Okay? So, if x is 0, this is 0 right here, everything here will turn to 0. If we plug in 0 here, all of this will become 0. And if we plug in 0 here, okay, this is 0 plus 1 is 0 is 1. And then 2 times 0 is 0 minus 1, so this is 1 times negative 1. It's actually negative 1a. So the first equation we'll have is 1 equals negative 1a or negative a. So therefore we can say that a equals negative 1. Now, what are the other value can we use? Okay, we can let x to be -1. So, if we plug in -1 here, all of this will, become 0. If we plug in -1 here, all of this will become 0 as well. So, but if we are going to plug in -1 here, we will have -1, 2 times -1 is -2, minus 1, -3, times -1 is +3. So that means 1 equals 3b, okay, which means that b equals 1/3. Okay, now what other clever values can we assign? We can let x be equal to 1/2. Okay, so if this is x is 1/2, this becomes 0. This part also becomes 0. And if we plug in 1/2 here and also 1/2 here, so this is 1/2 plus 1 is 3/2 times 1/2. This becomes 3/4. So that means we have 1. This here equals 3/4c. That means c is actually a 4/3. Okay. We all now have the values of A, B, and C. So we can now plug those values in here, the C here, the B here, and A. Let's go ahead and do that. So again, it looks like the derivative of x is just a 1, so we can now say this is just ln the absolute value of x. And here, this part here, it looks like the derivative of x plus 1 is also 1, so we can have 1/3 ln x plus 1. And in here, the derivative of 2x minus 1 is not 1, but it's 2. So that means we need a 2 here. And to compensate that, we can write 1/2 in here. Alright? So that we can simplify this into plus, okay, 4 times 1/3 times 2 is 4/6, which is actually 2/3. And now we can write ln absolute value of 2x minus 1, okay, of course, plus c. This is our answer for number 2.